All right, so we're going to have today's remote lecture since I'm not in town. We will cover this same material or very similar material in class, but this is to maintain continuity with the rest of the lecture recordings that we have. Before I begin the material, the American Chemical Society group here, they wanted me to share with you information about their third general meeting. So those are open to anyone who has interest in chemistry, and it's going to be Tuesday, March 7th at 7 p.m. in Fleming 160, and they do provide food to all of their meetings. So if you watch this recording or look at the notes in time, you'll have information about that, and I encourage you to attend if you're interested. They have a guest speaker from College of Pharmacy at this particular meeting. All right, so what we're going to cover today are some more things about aqueous solutions and chemical reactions that happen in aqueous solution. We covered last time the process of dissolving substances, electrolyte, non-electrolyte solutions, and that distinction, and talked a little bit about how we quantify the moles of ions that dissolve. And we're going to talk more today about quantification of solutions to begin with. But I did also forget about this. So we have our usual Try Hard Tuesday reminder of work habits. And this is just a reminder about making good use of office hours, if that's something that you think would be helpful to you. We have 214 or so people in the class, and I have here less than 5 as being regular office hour attendees. I think the reality is probably like 3 or less. I mean, there's very few of you that I see on a regular basis coming in here. So please take advantage of that, and if the posted times don't work for you to come and you want to still visit me, please just let me know. We can try to work out alternative arrangements. So you need to take the initiative. I'm always available for help, but I'm not going to seek you out. You have to come find me. So in terms of if you do decide to start coming, or what are some of the best practices, these are what a lot of the really effective students in this class do. It's good to keep track of all of the practice problems you've done in your homework attempts or practice homework attempts or what have you. If you're organized about that, it makes it a lot easier for us to go over things, and I can look at the work that you've done and help you understand. So bring those sort of things with you when you come. If you try to keep track of the work that you've done on homework problems, either in a physical notebook or a tablet. So if you bring those with you, I can see how you try to do the problem, and it's a lot easier for us to identify what mistakes you made or what you're not quite understanding. So that's helpful for me. I mean, you can come with any questions you have, any level of organization. I won't turn you away, but at the same time, if you're organized about things and bringing work with you that we can look over, it's very helpful for you, I think, and a lot of people do that. All right, let's go on into today's material. So I forgot to delete this slide. We actually covered this one last time, so I'm not going to do it again, but check the March 2nd notes for how we did this one, where we dissolved silver nitrate in water and it broke up into silver and nitrate ions, and we could quantify how many moles of those there are. So that's how it works for just talking about the number of moles of ions in solution. But the way that we usually quantify things in an aqueous solution is it's in a quantity called molarity. So molarity is a concentration unit. It tells us how concentrated the solution is. And it's another one of those intrinsic properties, which is not dependent on how much solution you have. It's a property of that specific solution, whether you have one drop of it or a whole ocean full of it. So what molarity is defined as is a new relationship involving moles. And it's given as moles of solute, so that's whatever's dissolved in the solution, divided by the liters of solution. So that's the specific volume unit we're using. It's moles over volume, and it has to be in liters for it to be defined as molarity. And it's again important to emphasize, not again, but for the first time, but I will emphasize it multiple times, that it's defined as liters of solution, not the liters of solvent that you use to prepare the solution. It's a minor distinction in most cases. Usually, whatever amount of solvent you use is approximately equal to the volume of solution you'll produce, but strictly speaking, the denominator in a molarity relationship is liters of solution. So this is a ratio of moles over liters, which then can be used then as a conversion factor, as we will not do too much today, but we'll see a lot when we start talking about stoichiometry of aqueous reactions. So the abbreviation for molarity is capital M. And so, for example, if we had 2 moles of solute and we dissolve that in 1.0 liters of solution, we would write this as a 2.0 M solution, sort of stated verbally as 2.0 molar solution. Capital M meaning molarity. So that means that capital M means moles per liter in that solution, moles of solute per liter of solution. And as I said, it's an intrinsic property, so if you made a solution in this way, whether you measured 1 drop of the solution or a huge bucket of it, the concentration and molarity would be the same. It's an intrinsic property. So let's just talk a little bit about how we calculate molarity then. It's pretty straightforward given the definition that we just covered. So if we take sulfuric acid, so we have 15 grams of that, and dissolve it in enough water to form 200 milliliters of solution, what's the molarity? The picture over here is just showing what happens if you put concentrated sulfuric acid onto sugar or paper or other sort of, starchy substances. It's pretty nasty stuff. It turns it black, basically chars it. But that's an aside. But what we're calculating here is molarity, capital M, which, as we said, is defined as moles of solute divided by liters of solution. So we need those 2 quantities to calculate molarity. And in this problem here, neither of these are given directly to us, but we can do pretty simple conversions to find them. So the first one is we need to find the moles of solute. The solute in this case is sulfuric acid. We have the grams of that, so we just have to convert to moles using molar mass. So to find the moles of solute, we take the mass that we're given, and then in combination with the molar mass that we're also given, we can convert into moles. So we have to divide by molar mass to convert grams into moles, a conversion that we did many, many times in chapter 5, and we'll still see from time to time. All right, so that's grams into moles, and that comes out to 0.153. So that's how much solute we have, and that's going to be in the numerator here. And then we need liters of solution. This is where we have to be a little bit careful about units, because very often solution volumes are measured in milliliters. It's a more convenient scale, I suppose, for chemistry laboratory purposes. But to calculate molarity, that needs to be in liters. We need to do a unit conversion for that. So the liters of solution, we have 200 milliliters. Now we have to remember that 1 liter is 1,000 milliliters. So we divide by 1,000 and get 0.200 liters as the denominator here. When we divide those two, we get 0.765, and then again we write it as capital M for moles per liter. All right, so that's how we calculate molarity. It's really just 2 quantities that you need, and the ratio of those 2 is how that would be defined. All right. Now, the next thing we're going to talk about, which is related to molarity, is a concept called dilution and associated calculations that deal with that. So let's first talk about what dilution is. And again, we're going to emphasize that we're doing this in terms of molarity, so it's going to be defined in terms of liters of solution whenever we're using these relationships. And so what dilution involves, let's just define it first, and we'll draw a little bit of a picture to show what it is. You add pure solvent to a solution. So again, you have a solution that's something dissolved in water. You add pure solvent. In our cases, it's going to be water pretty much all the time. And when you add the pure solvent to the solution, or you can do it the other way, you could add a solution into pure solvent, but you're basically just mixing those 2 together, solution with pure solvent. And what that does is it makes a new solution that has a lower concentration. So one way we can do this, so let's say we have a solution up here. So I'm going to use sort of blue to indicate the water, the solvent in this case. And then we have little solute particles dissolved in it, which I'll show as red dots. So I'm going to do about 10 of them. So those red dots are dispersed in the solution, dissolved. That would be our solute. Now what you do in dilution is you either pour pure solvent into this to make the concentration different, or you do it the other way around, which I guess is how I'm showing it here. So you'll pour this solution into pure water to then increase the volume. So that's what dilution would involve. You mix the two together, solution with pure solvent. And then when you do that, you're going to have still the same red solute particles present, but just dissolved in a larger volume of solution. So you'll still have 10 of those red solute particles. You're not losing solute when you do this. It's just going to be in a bigger volume. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So still the same number of solute particles, but now in a larger volume. So if you compare in a sort of qualitative and relative sense, these two solutions, the one that you're starting with has a larger molarity and a smaller volume. And then when you dilute it, you've increased the volume of the solution, but kept the moles of solute the same. So your molarity is going to be smaller and your volume is going to be larger after the dilution occurs. All right, so to kind of summarize that in words, basically the moles of solute stays the same before and after dilution, but it's the molarity and the volume that then are going to be different between the two solutions, the one that you've started with and the one after dilution. All right, so that's what dilution is. I think we have a pretty general concept of that from our everyday life. We kind of know what it means to dilute something to make the solution less concentrated, but it's important to recognize that when you do a dilution, you're just mixing the solution with pure solvent, and so the number of solute particles doesn't change when you do that. It's just the volume that they're occupying is now larger. So what that allows us to do is derive an equation for dilution, where we remember the definition of molarity is moles of solute divided by liters or volume of solution more generally. And so what that means is that if we cross multiply this, molarity times volume, if the volume is in liters, is equal to moles of solute. And because the moles of solute doesn't change during dilution, the initial number of moles and the final number of moles are equal, we can write this sort of before and after relationship, this before and after equation that describes it. The product of molarity and volume that we start with, M1V2, has to equal the product of molarity and volume that we end up with, M2V2. So M1V1 equals M2V2. The product of molarity and volume before and after the dilution are the same because the number of moles doesn't change during that process. So this is the dilution equation. So when you see a problem that involves dilution, which is usually going to be pretty clear from the wording, we're going to be using this equation. And again, the key thing with dilution is we're not doing a chemical reaction at this point. We're just changing the concentration of a solution by adding pure solvent. Okay, so let's do some dilution problems to see how this works. So one would be set up like this. What volume of 6 molar NaOH is needed to prepare 250 milliliters of 0.5 molar NaOH? And so essentially what we have is, in this problem, we're just changing the concentration of NaOH solution. We're not doing a reaction to change it into something else or anything like that. We're just going from a 6 molar solution to a 0.5 molar solution. So we're going to recognize that this is a dilution problem, and because of that, we have the dilution equation, M1V1 equals M2V2, and in a typical situation, 3 of these 4 terms are going to be known from the information in the problem or easy to find from that information, and we're just going to solve for the one that's unknown. So in this one here, we have the original molarity, which is 6 molar. That's going to be M1. We're looking for the original volume. What volume tells us that volume is our unknown, so V1 is our unknown, and then we're preparing a solution that has a final volume of 250 milliliters, that's our V2, and a final molarity of 0.5, which is our M2. So we have all of these except for V1, so with a little bit of algebra we can see that V1 is equal to M2V2 over M1. Now it turns out in problems like this, it doesn't really matter what volume unit you use as long as you're consistent as long as they're the same. So when we solve for V1 in this case and start putting the numbers in, M1 is we're going to do, M2 V2 over M1. So M2 in the top is 0.500 molar. V2 is 250 milliliters. So we don't have to convert that to liters. You can, but you don't have to. Usually we're going to want your answers in milliliters anyway, more often than not. And then in the bottom we have M1, which is 6.00 molar. So when we set it up this way, and we're cognizant of the units that we're using, molarity cancels out. Your concentrations for these, your molarities always have to be in molar units. That's really not any other easy way to do that. But then our volume is in milliliters, so when we solve this, that means the V1 that we calculate will be also directly given in milliliters. We don't have to convert into liters to do this. So that comes out to 20.8 milliliters. And so the sort of meaning of that number is that if we take 20.8 milliliters of 6 molar NaOH, and then we add enough water so that the final volume is 250 milliliters, the new concentration would be 0.5. And so that we're solving for is that number there, how much we would need to dilute to get to that final concentration and volume. All right, so that's going to be a pretty standard, pretty straightforward dilution problem. All right, let's go on then and start talking about chemical reactions that happen in solutions. So a big part of chapter 6, there's going to be 3 types of chemical reactions we're going to talk about, and we need to be able to understand them, balance the equations, predict products in some cases, and all that, and then eventually we're going to start doing stoichiometry with those types of reactions. So, but the big part of chapter 6, I would say the meat of the chapter is going to be defining and characterizing these different reactions. So the first one we're going to talk about is a precipitation reaction. And so what this is when you combine 2 aqueous solutions, usually of ionic compounds. So pretty much all the reactions we're going to talk about involve ionic compounds on some level, but especially precipitation reaction. That's going to be directly involving 2 solutions of ionic compounds. So, and then what happens in a precipitation reaction is one, or sometimes more than one, but usually just one, insoluble product forms. And so something that is no longer going to be able to be dissolved is going to form during the reaction, and it's going to form what's called a precipitate, meaning it'll fall out of the solution. Now, I don't know if you remember this far back, it was a while ago at this point, but one of the first days of class, I can't remember if it was the very first day or one of the first 2, definitely, I showed a video about conservation of mass where they mixed together 2 solutions and measured the mass before and after to show that it didn't change. And that reaction was actually a precipitation reaction. If you remember what it looked like, it was 2 clear colorless solutions. You mixed them together and this bright yellow sort of flaky powder formed and sort of crashed out of the solution. So that reaction is actually going to be what we're going to go through here. And so there's going to be sort of 3 steps we're going to take, though, to decide if a precipitate will form. So a big part of this section of precipitation reactions is to be able to predict if I mix together solutions of these 2 ionic compounds, will one of the products that forms, or more than one of the products that forms, will it be a precipitate, will it fall out of solution, will a precipitation reaction actually occur? So the way that we do this is it's going to be, the reactants are going to be 2 different ionic compounds, so we're going to separate them into their constituent ions. Or at least you need to think about what are the ions that make up those 2 reactants, whether you physically do this or not. So the reaction that we actually saw in the first day of class in that video, if you want to look back at it, was this one here. It was aqueous potassium iodide combined with aqueous lead nitrate. Now, from watching that video, you know that a precipitation occurs. There was a yellow solid that formed that was no longer dissolved after the reactions. That's a classic precipitation. So we're going to talk about how we would predict that there would be a precipitation and what the identity of that would be. So first we're going to think about the individual ions that make this up. And so potassium iodide is an ionic compound that's consisting of potassium plus and I minus. Again, we can use their locations on the periodic table to predict that they're +1 and -1 charges. And then lead here, the charge on lead is variable. We have 2 NO3 minus anions, which means that our lead is +2 in charge. So we do have to be able to review stuff we learned back in chapter 3 about predicting formulas and charges for ions and things of that sort. So make sure we don't forget all that. But those are the ions that make it up. Ki is made up of K plus and I minus, and then lead 2 plus and 2 NO3 minuses come from lead nitrate when it's dissolved in water. Then what we have to do is we have to figure out what are the possible products that can form from these ions. And so usually there's going to be 2 possible products, and the way that you find those 2 is by just swapping cations and anions. And so what I mean by that, so the first reactant Ki, the cation is K plus, and so the first possible product that can form is going to be that cation with the anion from the second reactant. So the second reactant has NO3 minus as the anion, so we're going to just swap those cations and anions. So K plus is going to be now paired with NO3 minus to form one of the 2 products, KNO3. And then the second product, we're going to take the cation from the second reactant, which is lead 2 plus, over here, and combine that with the anion from the first, which is I minus. And so the correct formula for that would be PbI2, because it's a lead 2 plus with 2 I minuses to balance the charge. So all we're doing when we're predicting the products of precipitation reactions, what's on the right side of the arrow, is going to be just to combine the cation from the first with the anion from the second, the anion from the first with the cation from the second. Just swap the cations and anions with each other. So we get these 2 possible products, but then we have to decide, okay, when we're going to write out this equation, we have to indicate whether there's actually a precipitate being formed. Is one of them insoluble or not? And so we have to decide whether one of these 2 products, KNO3, PbI2, or in rare cases both of them, are they going to be insoluble? And so for that, we have to know and understand what are called solubility rules. All right, so solubility rules are going to allow us to predict whether a specific ionic compound is soluble in water, meaning it would stay as an aqueous solution, or if it's insoluble, which means if it forms during a reaction, it's going to be a precipitate for that reaction. So your book just has sort of a laundry list of solubility rules, and if you just brute, and I have those reproduced here in the notes. So if you just brute force memorize those rules, you'll be fine. But I like to sort of divide things up a little bit differently and talk about things a little bit more systematically, just to sort of help internalize these rules. It's again, memorizing just a long list of rules is not the most satisfying way of learning things. So the first thing that I do is when you're looking at an ionic compound and trying to decide if it's soluble or not, there's going to be some cations and some anions that are always soluble, meaning that if they are part of that compound, whether as the cation or the anion, or whether they're both present, or either one of those is present in the compound, they are going to be soluble. Okay, so for the cations, what we have are, most of those are going to be the group 1A cations, which is that first column of the periodic table, which forms 1+ cations, so lithium plus, sodium plus, K plus, rubidium plus, and cesium plus. So for our purposes, if you have an ionic compound that has one of these cations in it, paired with any anion you can think of, we're going to assume that it is soluble. It's always soluble. And then the other one that falls in this category, there's just one polyatomic ion that falls in this, is NH4 plus, ammonium. So ammonium behaves the same way as these group 1As. There's essentially 3 anions that are also in this category. So nitrate, NO3 minus, perchlorate, ClO4 minus, and nitrate's the one that we'll definitely see the most often. I mean, all of these can show up, but the one that you're most likely to see is nitrate. And then acetate, which can be written as either CH3COO minus, or sometimes it's written as C2H3O2. However you remember that is fine, but that's called acetate. So again, these 3 anions, if they're present in the compound, no matter what the cation is, if this is the anion, nitrate, perchlorate, or acetate, then the ionic compound will be soluble, and it can't form a precipitate then. All right, now we also have some other ones which are always insoluble unless they're paired with the cation or anions from category A. So the cations that fall into this category are silver plus and lead 2 plus. So if you have a ionic compound of silver or lead, unless the anion is nitrate, perchlorate, or acetate, you will assume that it's insoluble. So any other anion, except for these ones up here that are always soluble, if you have it with silver or you have it with lead, it's going to be insoluble. And then we have some anions that are in this same category, where ionic compounds involving these anions are always insoluble unless the cation is one of these up here, group 1A or ammonium. So carbonate, any ionic compound of carbonate will be insoluble unless it's lithium, sodium, potassium, etc. Phosphate, sulfide, S2 minus, and chromate. So those 4 anions, any ionic compound of them will be insoluble unless the cation is one of these few up here. All right, so those 2 categories are the easiest to deal with, and they are going to come up in a lot of the different solubility rules and precipitation problems we do. But there are some other rules you still need to be familiar with that are a little bit more annoying because there's more exceptions to them. Okay, so here we have there's a few anions that are usually soluble unless they're paired with one of those category B cations. So those are going to be the halides, in particular the 3 heavier ones. So we're talking about the second to last row, second to last column of the periodic table, -1 anions, chloride, bromide, and iodide. Ionic compounds with those anions are usually soluble unless the cation is silver or lead, and there's also 2 other exceptions that are not going to be as common but are in our list of rules we expect you to know. So copper plus, similar to silver plus, makes insoluble halides. So copper halide, bromide, copper chloride, bromide, iodide, all insoluble. And the other one is this polyatomic dimercury, this weird cation, Hg2 2 plus. So it's 2 mercury plus 1s bonded together into a diatomic cation. But anyways, halide salts of those are also insoluble. So lead, silver, copper, mercury make insoluble halides, bromide, chloride, or iodide. Pretty much all other ionic compounds of those anions you would assume are soluble. And then this last category here are the ones that are kind of annoying. Now, as it turns out, these 2 actually have the same exceptions, but just they work in sort of the opposite direction. So the first one we'll talk about is sulfate, SO4 2 minus. Ionic compounds involving sulfate are usually soluble, but they have several exceptions. So they're going to be soluble except if they're paired with category B, which would be those ones up here that are always insoluble, silver and lead. So those will be insoluble, as well as the heavier group 2 cations. So I should probably flip back to the periodic table more than I have been, but these heavier group 2s, calcium, strontium, barium, they also make insoluble sulfate compounds. So calcium 2 plus, strontium 2 plus, and barium 2 plus, the heavier group 2As, are insoluble with sulfate. Those are exceptions. But in most other cases, sulfate would be soluble. And then OH minus kind of works in the opposite direction. It's usually insoluble, so most hydroxide compounds are insoluble, except with category A, which is going to be the group 1A cations that are always soluble. So again, that rule takes preference anyway. Or the same 3 exceptions, but this time they work in the opposite direction. So the heavier group 2 hydroxides, calcium, strontium, barium, are soluble, even though OH minus hydroxide compounds are usually insoluble. So there's no real easy way for me to teach those to you, but I think by breaking them down in these categories it helps. And especially if you can look for ions that are in one of these first 2 categories here, that can help you immediately identify it as soluble or insoluble. The rest of these are a little bit more difficult to deal with, but likely won't show up as often either. And here's how they're written in the book. Again, they're not as systematic, I think, so I like the way that I do it, but however you choose to learn them is totally fine with me. So then once we have an aqueous ionic reaction that could involve precipitation, we're going to, there's different ways that we can write out the equation, and now we're able to use the solubility rules to predict which compound would be formed as a precipitate. So probably the most common way that we'll see it is called the molecular or formula equation. And in a molecular or formula equation, you have the full set of reactants and products, and they're all written as sort of intact species. You just write them in their normal, formula way that you would write them out. So you don't separate any ions or anything in this. So reactants and products are written as, intact species with their full chemical formulas given. So for the one that we've been talking about, potassium iodide and lead nitrate, you would have Ki as an aqueous solution reacting with lead nitrate as an aqueous solution. And then, as we said, the products of this are going to be swapping cations and anions. So K plus is going to pair with NO3 minus to make KNO3. And then lead Pb2 plus is going to pair with I minus to make PbI2. So we need some coefficients to balance this. And so what we need are, let's see, we have 2 nitrates, so we're going to need a 2 there. We have 2 iodides, so we're going to need a 2 there. So usually with precipitation reactions or acid and base that we're going to cover later today, coefficients are generally pretty small, 1, 2, 3, not usually much higher than that. So we just need those coefficients. And then the last part of an aqueous reaction that's important is indicating which reactants and products are aqueous versus which ones would be another state of matter, usually as an insoluble product. So the 2 reactants are always aqueous. We're mixing together 2 aqueous solutions. That one's obvious. And then on the product side, we use solubility rules to predict which of the 2 products would be dissolved in solution and still labeled as aqueous versus which one would form a precipitate and then need to be labeled as a solid. So from solubility rules, all potassium salts and all nitrate salts are soluble. So KNO3 is definitely soluble, and we write it as AQ. But as we said, lead 2 plus, most lead 2 plus compounds are insoluble unless there's one of those special anions, nitrate, perchlorate, or acetate. So this would be our insoluble product. This is our precipitate, and that would be labeled as S for solid. It's no longer dissolved in the solution. And so if you again think back to the video from day 1 or look back at it again now, the reaction formed that yellow solid that it was clearly easy to see, and that's going to be this one here, the lead iodide, lead 2 iodide. Now there's 2 other ways though of writing ionic equations. Another one is called total ionic equation. This one's not particularly useful by itself, but it's sort of an intermediate between the molecular equation and the net ionic, which are the 2 most common ones. So the total ionic equation, what you do is you separate all soluble ionic compounds or strong acids when we get to those. But anything that dissociates into ions when it dissolves, anything that forms a strong electrolyte, you separate those, anything that has an AQ next to it basically, or it would be a strong acid if it's an acid, you separate those into their individual ions. So in this reaction up here, if we have Ki aqueous, that means it's going to be dissolved as 2K plus and 2 I minuses. And then our lead nitrate is aqueous, so when that dissolves, as we already talked about a little bit, it's going to be lead 2 plus and 2 NO3 minus. So on the reaction side, we separate everything out into ions because everything is dissolved. And then in the product side, we still see that KNO3 is written as aqueous here. So we're going to separate that into its ions as well. K plus NO3 minus, 2 of each because of the coefficient. So it's going to be 2K plus and 2 NO3 minuses. But then the last product, lead iodide, is no longer soluble. It has an S next to it. So for an ionic equation, we don't want to separate that because it's not dissolved in the solution as ions. It's going to be an intact solid, PbI2. So that one we leave the same. And then finally, to get to the net ionic equation, which is also a fairly common way of writing things, we have to remove what are called the spectator ions. Those are going to be the ions that appear on both sides of the arrow as aqueous species. So we remove spectator ions to convert it into a net ionic equation. And again, those are the ions that appear on both sides of the arrow. So going back up to the total ionic equation, we see that we have 2K plus here on the left side and 2K plus on the right. So K plus is one of our spectator ions. And then we also have 2 NO3 minuses on the reactant side and 2 NO3 minuses on the product side. So that's another spectator ion, NO3 minus. So for the net ionic equation, we get rid of those ones, and we're just going to write, usually we write cation first, then anion. So we'll write Pb2 plus as the cation on the left, 2 I minuses as the anion, and then those combine to form the insoluble product PbI2. So for a precipitation reaction, the net ionic equation is going to basically just show the two ions that combine to make your insoluble precipitate. So in this case, it's lead 2 plus and I minus that are left in the net ionic equation. And that leaves K plus and NO3 minus as our spectator ions. They're going to be aqueous, dissolved on both sides, and so they don't in net participate in the reaction, so they're classified as spectator ions. All right, so again, there's K plus and NO3 minus, the two spectator ions. All right, so that's how we write out the equations for these precipitation reactions. So let's do one or two examples of this. Just one, I guess, because we're trying to keep things moving here. Write the molecular, total ionic, and net ionic equations for the reaction between sodium sulfate and silver 1 nitrate. All right, so there's a lot going on here that we have to keep straight. So let's start with the molecular equation, where we just write out the formulas of all the reactants and products, don't separate anything into ions. So here we have to translate words into chemical formulas, something we've had to do quite a bit since chapter 3. So the first reactant is sodium sulfate. So if we've already forgotten, sodium is right here on the periodic table. Because it's in the first column, it should be a +1 cation. And then sulfate, we have to remember, is SO4 2 minus. So this is Na plus, this is SO4 2 minus. And so that means the first reactant is going to be Na2SO4. Now, as I said, anything on the reactant side is going to be aqueous, because we're always talking about reactions that involve two aqueous solutions. And we know from solubility rules that Na plus all sodium salts are soluble. So we can definitely say that that's going to be aqueous. The second reactant is silver 1 nitrate. So silver is Ag. I guess that's beyond where you need to know in the periodic table, so we should have told you that in this problem. So silver is there, Ag. +1 is the most common cation for silver. So it's silver 1 +1 nitrate, which is NO3 minus, so the formula for that would be AgNO3. Also aqueous, all nitrate compounds are soluble. The reactants in these cases will be both aqueous. And then what we form as products, we're going to just swap cations and anions. So the Na plus sodium pairs with NO3 minus nitrate to make NaNO3 is one product. We're just swapping the cations and the anions. And then the second product is going to be silver Ag plus with sulfate SO4 2 minus. So that's going to have to be Ag2SO4 to be charge balanced. I should move that over a little bit because I don't have enough room. Eventually I'll get it right. Ag2SO4. Okay. Now we still haven't finished this completely yet, because there's two things we have to do. We have to put coefficients in to make sure it's balanced, and we have to indicate on the product side which ones are aqueous, which ones are solid or otherwise. So we can do that in either order, but if we think about solubility rules first, all sodium salts are soluble, all nitrate salts are soluble, so that's going to still be AQ, aqueous. But then for silver sulfates, almost all silver salts are insoluble unless nitrate perchlorate acetate is the anion. So silver with sulfate will be insoluble, so that's going to be marked as solid. And then in terms of coefficients, we have 2 silvers in this product, so we need 2 sodium nitrates. We have 2 sodiums in this reactant, and so we need a coefficient of 2 there in front of sodium nitrate to make sure we have the same number of ions on each side. So again, coefficients are usually small for these. So that would be the molecular or formula equation. To go to the total ionic equation, what we again have to do is separate everything that's aqueous into its respective cations and anions. So on the left side, we're going to separate both things because they're both aqueous. So sodium sulfate is going to separate into 2 Na pluses, a sulfate, SO4 2 minus, And then silver nitrate is aqueous, so it's going to form 2 Ag plus because there's a coefficient of 2 in front of it. 2 NO3 minuses, the coefficient of 2 applies to both of those. So that's the left side where we've separated everything. And then the right side, we have to separate the products that are aqueous as well. So sodium nitrate is soluble, so it's still going to be listed as aqueous. We're going to have 2 Na pluses, 2 NO3 minuses. And then the one, though, that's the solid, that's the precipitate, silver sulfate, we don't separate because it's not dissolved anymore. So Ag2SO4 will still stay together and still be written as a solid. Gave myself barely enough room there. All right, so that's going to be how we write the total ionic equation, where we separate everything that's soluble into its ions. And then finally, for net ionic, you're going to take out the spectator ions. So we have 2 Na pluses on both sides, so sodium is a spectator ion. We have 2 NO3 minuses on both sides, so nitrate's a spectator ion. And what that leaves us for the net ionic is 2 silver plus. Conventionally, we write cations first, so you don't necessarily have to. SO4 2 minus. Aqueous ions on the left side, combining to form solid silver sulfate, which is our precipitate. All right, so very similar as the last one, just different ions involved. And again, the key is to identify the insoluble product using solubility rules. All right, so that's the gist on precipitation reactions. There's probably some other subtle details that you'll need to pick up on your own, but that should cover most of it. The second major reaction type we're going to talk about are acid-base reactions. And we kind of, at this point, we have an idea of what an acid is. At least we know how to recognize it from its formula and how to name acids, which we learned in chapter 3. But we need to talk a little bit more about the precise definition of acid and what happens when we dissolve them in water. So an acid, the simplest definition of an acid, there are others that you'll cover in Chem 2, but the simplest definition that's fine for what we're going to do in this class is it's a compound that releases H plus when it dissolves in water. So it's a covalent compound, but it behaves kind of like an ionic compound because when you dissolve it in water, it does produce ions, and one of those ions will be H plus. So the general formula for an acid, they always start with hydrogen, some number of hydrogens, and then with some anion X. So X would be the anion that's paired with H plus, which would then also be released into the solution when the acid dissolves. And then N here, which is the number of hydrogen atoms in the formula, that's going to be the charge on the anion. Basically, you need enough hydrogens in the formula to balance whatever the charge is on the anion. All right, so acids we're already a little bit familiar with because we talked about how to name them earlier. We have not seen anything yet with bases. And so a base is going to be defined as a compound that releases OH minus when it dissolves in water. So when you dissolve a base in water, it produces hydroxide anions, OH minus. So most bases that we'll deal with in this class, the most common ones and the ones that you'll see all the time, have the general formula of a metal cation with just hydroxide anions. So basically they're just ionic compounds involving hydroxide. Where in this, again, N is the charge of whatever the charge compensating cation is, the M, the metal cation. All right, so bases are essentially just going to be soluble hydroxide compounds. So usually metal is going to be, group 1, because those are the ones that are most commonly soluble. So like sodium, lithium, potassium, and so on. Or as we talked about, some of the group 2 hydroxides are also soluble. So any hydroxide compound that dissolves in water can function as a base because when it dissolves, OH minus separates into solution, and that's going to be what defines it as a base. All right. Now we also, within acids and bases, we can categorize them as either strong or weak. This is something that we also talked about just a little bit last time when we were talking about strong and weak electrolytes. But a strong acid or a base is going to be an acid or a base that completely dissociates when you dissolve it in water. So it separates completely into its ions when it's dissolved in water. So it dissociates completely into ions And as we know from last time, that would produce then a solution that's classified as a strong electrolyte solution. It conducts electricity really well. So the strong acids that we have, which we did introduce last time, and we'll just review here quickly, the acids that behave as strong acids are going to be the 3 heavier halogen acids, HCl, HBr, HI, and then 3 oxo acids that have these oxo anions, so nitric acid, perchloric acid, and sulfuric acid is also a strong acid. So those are our 6 strong acids that we definitely need to know. Most other acids, or any other acid that we encounter, we would assume is a weak acid. And then for strong bases, any of the soluble hydroxide compounds would be classified as strong bases. And since a lot of hydroxide compounds are insoluble, those that are soluble and classified as strong bases are all of the group 1 hydroxides: lithium, sodium, potassium, rubidium, and cesium. All of those group 1 hydroxides are soluble, and so they would be classified as strong bases, because when you dissolve them in water, they completely separate into the cation and the hydroxide anion. And then the heavier group 2 hydroxides are also soluble and classified as strong bases. So calcium, strontium, and barium. So those are our strong bases, and it's usually a pretty dead giveaway because they all have OH directly in the formula. Now, weak acids and bases are those that do not completely dissociate, so they're going to form some ions when they dissolve, some H plus if it's an acid, some OH minus if it's a base, but most of the molecules are going to stay intact and still remain as sort of charge neutral and not producing ions. So these are going to be weak acids and bases do not completely dissociate. And so what that means is that in a weak acid or base, most of the molecules remain intact. They do not separate into ions or produce H plus or OH minus. Most of them stay together. And I'm writing this completely wrong. Most of the molecules remain intact when you dissolve a weak acid or a weak base. So for the weak acids, it's going to be, most other acids or any other acid besides the 6 listed above. So the common weak acids are HF, the other halogen acid that's not a strong acid. HCl, HBr, HI are all strong. HF is weak though. Phosphoric acid is a classic weak acid that's very common. And then acetic acid is another very common one, CH3COOH, or sometimes written as HC2H3O2. I'm not used to writing it that way, but that's also another way of writing acetic acid. So same compound. This formula here tells you a little bit more about what the structure is, so it's more descriptive. And then the only weak base that you guys need to know about, there will be more of these in the future if you keep taking chemistry. This is not the only weak base in the world, but for this class, just remember that NH3 is a weak base. Now, it might not be obvious why this is. You're thinking, well, a base has OH minus in it. You just told me that. So why is NH3 going to be a weak base? Well, the reason, which you'll talk about in more detail in Chem 2, but the reason it's a base is because when you dissolve NH3 in water, a small percentage, again, not all of them because it's a weak base, but a small percentage of those NH3 molecules are going to react with the water that's always present because it's an aqueous solution, and that's going to form NH4 plus and OH minus. So again, you're producing OH minus, which is why NH3 is classified as a base. So some small percentage in reality of the NH3 molecules react with water, and an H plus from water transfers to the NH3. So that makes NH4 plus, and then that releases OH minus from the water. Okay, so that's how ammonia NH3 would be classified as a weak base. So that's what acids and bases are. Now let's talk about how they react with each other. So the net ionic equation for any acid-base reaction is essentially the same. There's some cases where the net ionic equation is a little bit more complicated if a precipitate is also produced. So acid-base reactions can also result in precipitation. But the one thing that always happens when an acid and a base react with each other is that the H plus from the acid combines with OH minus from the base, and those are going to combine to form H2O. H plus OH minus makes H2O as a liquid. All right, so that would be the Ionic equation when you have a strong acid and a strong base. If weak acids or weak bases are involved, the equations look a little bit different. And if precipitation happens at the same time, that complicates things. But in general, whenever you have an acid-base reaction, this is what's happening. H plus OH minus combine to form H2O. So there will be some spectator ions involved that are going to depend on what the acid and the base are. As well as, you know, in the full equation anyway, the coefficients also depend on what the acid and the base are. But these are, in a lot of ways, similar to precipitation reactions. Two aqueous compounds reacting and then forming two products. One of them is water, and as we'll see, the other one is ionic compound. And then, you know, you have to use sometimes solubility rules to identify whether that is, you know, going to involve precipitation or not. But the overall outcome then would be acid and base on the reactant side. And then on the product side, on the right side of the arrow, you have water as one product and the ionic compound as the second product. And so the ionic compound that forms, the cation comes from the base. And in particular, if the base is, you know, a hydroxide compound, whatever that cation was that was with hydroxide, usually lithium or sodium or something like that, that's going to be the cation that's involved in the product. And then the anion in that compound is going to come from the acid. All acids have an anion associated with H+, and so that anion ends up as an ionic compound on the product side. So that's really what every acid-base reaction looks like. And as I said, there's some similarities to precipitation reactions. Two reactants forming two products, but in this case, only one of the two products is an ionic compound, but you still need to use solubility rules to decide if it's, you know, going to precipitate or not. In most cases it doesn't, but it can. All right, so let's talk about some examples then and how we sort of balance these and write out the coefficients and everything. So if we have nitric acid with potassium hydroxide, nitric acid is HNO3, so that's our acid. And then potassium hydroxide, remember that potassium is K, which is K+, hydroxide is OH minus, so the formula for potassium hydroxide is just KOH. So those are the two reactants, acid plus base, and you're always going to form two products, water as a liquid, and then an ionic compound. So the ionic compound that forms is going to have the cation that's left from the base, which is K+, the anion that's left from the acid, which is NO3 minus, so it's going to form KNO3. And we know from solubility rules that all potassium salts are soluble, all nitrate salts are soluble, so that's definitely going to be in solution at the end of AQ. Now in terms of coefficients, this ends up being a reaction that doesn't need any coefficients. Everything is 1 to 1 to 1 to 1. The way that you can look at it for acid-base reactions, you can certainly just do it by inspection, making sure the atoms balance on each side. But a helpful way to investigate it is to think about, okay, how many H pluses does my acid have? It has 1, HNO3. How many OH minuses does my base have? It has 1, KOH. So if you have 1 H plus and 1 OH minus, those are going to react together in a 1-to-1 ratio, and they're going to form 1 mole of water. And so then all that's left is to make sure you have the right coefficients on your ionic compound, one of each ion, so there's no coefficients needed. So there are some acid-base reactions like this one where everything has a coefficient of 1. Now they can get slightly more complicated. So if we have sulfuric acid with potassium hydroxide, sulfuric acid comes from sulfate, which is SO4 2-, so this formula for the acid is H2SO4. And then that's going to combine with KOH, again, potassium hydroxide, same base. And on the product side, what we're going to have is we have water again, always a product for an acid-base reaction. And then the ionic compound that's involved, we take the cation, which is K+, and the anion, which is SO4 2-. So the correct formula to balance those would be K2SO4, potassium sulfate. All potassium salts are soluble, so that's going to be aqueous. But in this equation here, we need some coefficients to balance things out. And again, the way that I like to do it is to look at the H plus and the OH minus first. So our acid in this case has 2 H pluses in the formula. And so if we have 2 H pluses from the acid, we also need 2 OH minuses from the base to completely react. So that requires a coefficient of 2 here. And if we have 2 H pluses with 2 OH minuses, we will form 2 moles of water. This product here doesn't need a coefficient because we have 2 potassiums here, 2 from the reactant side, 1 sulfate, 1 sulfate. So no coefficient on the last one, but we need coefficients of 2 on KOH and H2O to make sure we have the correct number of OH minuses to react and to make sure we're forming the correct number of water as a product. All right, so that's a slightly more complicated example, but most acid-base reactions, you're going to have coefficients of 1 or 2, maybe 3 at the highest, just like precipitation. They don't usually have very large or very complicated coefficient combinations. Now, the last one we're going to do here is how things change a little bit if we have a weak acid. So what we're going to eventually produce is the net ionic equation for a reaction between acetic acid and barium hydroxide. Okay, so acetic acid is a weak acid. So if we're just writing out the full equation, the molecular or formula equation as it's called, doesn't really change much or really change at all when we're dealing with a weak acid. It's going to look almost the same as any, or really the same as any other acid-base reaction. So if we have acetic acid and then barium hydroxide, which I should have told you barium is Ba, but I think we are familiar with that one by now. But barium hydroxide, Ba here is way down here, so you wouldn't have to know it, but that's in the second column of the periodic table, so it's going to be a 2+ cation. So barium hydroxide is going to be BaOH2, also aqueous. On the product side, it's going to really look identical to any other acid-base reaction. It doesn't really matter that our acid is weak in this case, because what you form is still going to be water. And then you're going to still form an ionic compound that involves the cation from the base and the anion from the acid. So the cation from the base in this case is barium 2+, and the anion is CH3COO- acetate, which you can write in different ways, but I'll write it in this way just to keep it consistent. And that's going to be soluble because acetate salts are always soluble. But we have to have some coefficients here as well. So we have, in this case, we have 2 OH minuses in the base, so we need 2 H pluses. Acetic acid only has 1 acidic hydrogen. It's again, you can see that more clearly if you write it as HC2H3O2. Acetic acid only has 1 H plus in the formula. The other hydrogens are not active in the acid-base reaction. So we have 1 H plus, 2 OH minuses. So we need a coefficient of 2 there to balance those, which then gives us a coefficient of 2 in front of water as well. So a couple of coefficients, but that would be the total ionic, or the molecular equation. Pretty easy to do for weak acids as well. Really nothing different than strong acids. But when we write the total ionic equation, this is where we have to be careful when we're dealing with weak acids or weak bases. We have to recognize that because acetic acid is a weak acid, it's only going to dissociate a little bit in water, and so we don't want to write it out and separate it up into its ions. It's a weak acid, and so when we write out the total ionic, our acetic acid here we're still going to write as CH3COOH. The majority of the molecules, the vast majority as it turns out, in any weak acid are going to still be intact. So we don't want to separate this into ions when it's a weak acid. Now the barium hydroxide, though, that's an aqueous ionic compound, so that we can separate out into barium 2+ and 2 OH minuses. And then on the product side, what we have is still water. Water is not an ionic compound or a strong acid. It's the liquid, as we've indicated. So that one's going to stay together. And then our other product, which is barium acetate, is also an aqueous soluble compound. So we're going to write that as its 2 ions, barium 2+ and 2 acetates when it dissociates, so CH3COO-. All right, so that's our total ionic equation. And again, a way to be careful about with weak acids is we don't separate them. Strong acids we would. So if we had HCl as our acid, we would separate that in the ionic equation to H+ and CO-. Because it's strong, we have 100% dissociation. But for weak acids, most of the molecules, almost all of them, remain together, and so we don't separate those. So when we're putting together then the net ionic equation, in this case, we only have one spectator ion. The only ion that appears on both sides as an ion is barium 2+. So that's our spectator ion, but OH- only appears on the left and acetate only appears on the right, so that's the only spectator ion is barium 2+. So our net ionic equation doesn't simplify all that much. We just remove the barium. And so what we have then for our net ionic is acetic acid, again written together because it's a weak acid, not dissociated, 2 OH minuses forming 2 waters and 2 acetates. Now what you might also recognize is that once we did this, our net ionic equation is not as simple as it could be because we have coefficients of 2 in front of everything. We need those coefficients of 2 to balance the full equation, but now that we've written it as a net ionic equation, it can be simplified to just coefficients of 1. So we can reduce it to the smallest whole number coefficients, where we get rid of all these 2's because there's a 2 in front of everything, so we can just write it as a 1-to-1-to-1 reaction. So acetate, sorry, it's still acetic acid. Acetic acid plus OH minus, so this is we get rid of the 2, so it's just going to be 1 water and 1 acetate ion. So we got coefficients of 2 in front of everything when we produce our net ionic, so that can simplify to just have the coefficients of 1. All right, so it gets more complicated with weak acids when we're asking for net ionic equations, but we just, remember the concepts that we've covered. Ionic equations, you separate everything that's dissociated into its individual ions. So that's going to be soluble ionic compounds or strong acids, but if it's a if it's a covalent compound, if it's a precipitate, if it's a weak acid, those are not separated in solution, so you're going to write those as intact molecules, as intact formulas when you're producing those types of equations. All right, so I think that takes us to the end of today's lecture. Probably a little bit shorter than a normal class because I didn't really pause for questions or anything like that. So if you have any questions on this material, please get in touch with me. It was covered in class at some level by Professor Galloy, but this hopefully will help you stay up to date on everything and keep continuity going with the rest of everything else. All right, so again, I apologize for being gone this whole week, but you guys are in good hands, and I wish you the best for the rest of the week as well as a good spring break.